Was our last glacier event across the state probably 25, 30,000 years ago. Would that have been our last one, Penny?
Yeah.
Something like that. It didn't reach here. It came, I think, about mid-state or the top 2/3 of the state. It didn't reach where we are. Our previous glacial events were probably, what, 1 million years ago or something that were in this area.
And we looked at that. I showed the
Okay.
extent of the Kansas and the Wisconsin.
Okay. So yeah, she knows all those names for those. I don't remember all those names. So at any rate, the glaciers move a lot of things around. At some point, they get far enough south, it's starting to warm up a little, and they're melting about as fast as they're grinding along. And then pretty soon they start melting faster, and the next thing you know, they're gone. And they leave all this stuff around. And so that's when the swell formation process would begin. We do have also deposition of materials from alluvial deposits, outwashed from the glaciers, running water, still water. So water moves a lot of things around, and it ends up in a certain spot. For example, in this area, the glaciers were receding, whenever it was, many years ago or so, and there's torrents of water just going everywhere across the landscape, carrying large rocks. Some of it's moving fast enough, that water's moving fast enough to carry rocks around. Well, as soon as it comes out of the channel, it starts to slow down, and immediately that stuff drops out. And the further away from that source, that channel, the finer the material. And so you get a little bit further away, and then you got some sand deposits, they're falling out, and then the next thing you know, the water's pretty still, and it meanders up a little slough somewhere, back on a terrace, and it just sits there, and it evaporates, and it leaves the clay behind. And that process goes over and over again. So if you drive down River Road, you'll see the gravel mines. So that's close to that original current. So there's, you know, an endless supply of gravel. And there's a couple gravel companies there that are pulling that stuff out, and they sort it, and they have piles of sand, and they have piles of rock and stuff like that. And if you move on a little bit further east, away from the Wabash River, you get into our sand hills. Now, those were not deposited by water, that's wind. So the sand was originally down there on a low spot somewhere, and then the wind picks it up and starts blowing it to the east. And the wind obviously starts slowing down at some point. So the sand hills are relatively close, within about a mile or two of the Wabash. That's where our melon crops and specialty crops and stuff are on those sand hills. And then as it moves on to the east, now the sand is gone, and it keeps moving, and the next thing you know, it's dropping out silts. So if you go another few miles east in Knox County, on our uplands, those are all wind-blown silt deposits. So that's all parent material. You know, landscape was reworked by glaciers, the glaciers are gone, it dries out, water moves things around, wind moves things around, and we've got this glob of stuff on the landform, and then the soil begins. So that's time zero for soil. Whatever that deposition was, and it got laid down, and then things are stable, and there's no more upheavals, there's no more flooding, there's no more glacier, massive catastrophic geological events. And so the soil then begins to form, and that would be time zero. And from there, it goes, lichens and young plants and stuff will invade, and we get a little topsoil developed, and the next thing you know, there's some other processes going on, and you get a soil profile. So let me run you through, let me back up here. Let's see, I already never did set this back, so.
Okay.
Oh, that's good. We can show them this right here. Yeah,
okay.
I'm glad you had that up. So,
okay.
Yeah, right here, let's see, where's my legend? I can't read it. Thick lust deposits, number 5. And that's the lion's share of Knox County. That's our uplands right there. The little brown band, that should be our sand hills. Can't read that. You guys maybe can read it better than I can. That's a number 4. Yeah, that's our Aeolian sand. So that's our little thin band of sand hills which reside between the water-worked parts, which are number 3. Number 3 is the alluvial and outwash deposits. So that would be stuff either gushing away from the melting glaciers or some of the finer material that gets picked up and moves around in normal river activity. You know, the Wabash River floods a few times every year, and it leaves material out there on the terrace. And so those tend to be rather young soils, because every time the river floods and comes onto a terrace area, it's carrying a silt load from upstream somewhere. It'll slow down and dump some of that out, and if it's moving fast, it might pick some more up. So there's an exchange of materials going on the terrace, on the terraces of the river systems around the state, and that's just the way they work. So we've got our 3 main parent materials here. We got the water allayed materials, either alluvial or outwash from the glaciers. And if it's outwash, it will have some gravel in it, and that's where the gravel mines are. If it's alluvial from the river, it's pretty fine, or kind of a medium to fine texture soil. And then we have our sand hills. That's the number 4. And it's not a very thick band, you can see, but it does have a concentration of specialty crops. And then all the rest of us are the uplands of the silt loams. Those are our deep silt loam soils, wind-blown silts. We call those loess deposits. And so those depositions result in very different soils, you know, that will develop in them. This one here is interesting, number 11. That's our loess over weathered sandstone and shale. And then we also have loess over the limestone deposits, which is 12. So when you look at areas 11 and 12 on this map, those are the hills, you know, the scenic hills of southern Indiana, where we have the recreational areas and the camping and the hunting. The Hoosier National Forest is in that area. Those are very, very old soils. And those hills are still there because the glaciers didn't cut them down. You know, the glaciers didn't run over the top of them. So those hills have been there for a while. Benny could probably tell you exactly how long, I don't know. But they do represent our oldest soils in the state. And they developed in that residuum either limestone, which is number 12, or the sandstone and shale, which is number 11. And they give rise to different kinds of soil types, but both of those are very, very old profiles. However, you do notice it says something about discontinuous loess, which overlays that, you know. So when we back up here to the source of the loess, or those wind-blown silts, we're right in here. You know, the glaciers receded, the silts are there, everything dried up, prevailing winds from the west start blowing that stuff across the landscape. And as you can imagine, the closer you are to the source, the thicker the deposits will be. So we have some really, really thick loess deposits here in Knox, Gibson, Posey County, all this even up into Sullivan, this whole area through here. They can be 20, 30 feet thick of just wind-blown, just big old piles of silt out there on the landform. As you move east, that gets thinner and thinner. So by the time you get over here, the loess cap on these zones 11 and 12 probably isn't over 18 inches or so thick. Well, let's say 18 to 24 inches thick, depending on the amount of erosion and the conditions under which it was deposited. So now we've got 2 parent materials over here. See, we've got the original residuum, either limestone or sandstone, and it's got a loess cap on it. So we've got 2 parent materials, which give rise to unique soils. And we call this our fragipan area. Fragipans are very common over here. It takes a few 100,000 years probably to get a fragipan, and it's typically developed under deciduous hardwoods. And of course, you know, we probably have some of the finest hardwoods in the country, if not in the world, here in those forests of south central Indiana. So those are very unique soils, very, very old soils, and it would have very different characteristics than the soils that we have over here in our neck of the woods.
Yep. For those people that aren't from southern Indiana,
Oh, that would be watermelons. That's our main one. Cantaloupes, sweet corn, pumpkins, yeah. Just about squash and vegetable. There's all kinds of stuff, yeah, that people do on the sand hills around. And if you think about it, those sand hills don't really lend themselves very well to corn and soybeans unless you have irrigation. But again, you're in the hills, so irrigation systems sometimes don't work so well if it's not real flat, you know. So the specialty crops are intensively managed, very, very high investment, and a very, very high return. So there is some risk there that your average corn and soybean farmer probably doesn't assume. I mean, all farming is risk for sure, but your investment on a per acre basis for average corn soybean production is very, very probably 10 to 20% of what an investment would be for an acre of watermelons or cantaloupes, or we grow potatoes and sweet corn and, as she was saying, pumpkins, the squash, all those things. Those are really, really high investment upfront crops. They require intensive management. So, you know, I'm a field agronomist, so I identify better with corn and soybean growers, and we plant our crop and make sure we got enough fertilizer on it. We do a few things of maybe we might spray it, maybe, you know, some farmers will fly on some fungicides and maybe other farmers don't. So it's a pretty routine, non-intensive, what we would call extensive type of management on those soils. And our silt loams are great for that. You know, they're deep, they hold a lot of water, and so they're very, very good for the routine corn, soybean, winter crops of wheat or whatever production. However, on the sand hills, those things drain. It can rain a couple inches, and within a day or two, they're dry again. You know, well, they're not dry, but they're not holding a lot of water. So a crop like corn uses copious amounts of water, and the sand hills just simply don't hold enough. And so you'd have to irrigate it, but that doesn't work so well on corn, especially with depressed commodity prices like we have now. But the specialty crops are really, really good for there because you have the high investment. You can put the perforated trickle tape under that plastic. You can water them, you can fertigate through that, you can intensively manage them, and then of course we have a traditional production of truck crops, I would call them, or you know, the vegetable, the melon industry is historically tied to this area. It's been here for a long, long time, generations, and so we do have a reliable, except maybe this year because of COVID, we generally have a reliable supply of migrant labor because it does depend on intensive labor. And so the migrant, and we do have an influx of migrant labor, comes through and helps us, you know, finish off those specialty crops. So you can't do that, of course, with other commodities, but specialty crops lend themselves very well to the sand hills. Things like watermelon love that oxygenated rooting environment. It's well drained, have a lot of oxygen around the root, and so they do very, very well. Add a little water, add a little fertilizer, and they do quite well. Okay, at any rate, sorry for getting sidetracked there on that, but that helps us, I think, right here in our little neck of the woods. We have a wide variety of soil types, from residuum, and then wind and water. We got to get up here to the central part of the state to get more into the glacial till plains. Let's see, number 8 is thin loess over glacial till. So that was from the recent glacial event of 25,000 years ago, whatever. And number 7 is clay glacial till without the loess cap on it. So you can see the change from going from here, from our neck of the woods, just you know, halfway up to in the middle of the state. Now we've gotten away from our wind and waterworks soils. Now we're up to direct glacial deposits, and so those soils are very different. If we get over here into this part, number 8 is, oh, it's the same. Maybe I forget what predominantly prairie soils. That's what I was looking for. See that little crossed shaded area right up here? So that's about as far east as prairie grasses come. If you go across Illinois into Iowa, of course, you get the tall grass prairies. We have mainly trees in Indiana. So from here east, it was mainly deciduous hardwoods, which gives rise to a different soil than if you have prairie grass as the native vegetation. So there's a lot of things that influence the soil type that you're going to get. The parent material that you start with, of course, has a big influence. And then what's the native vegetation? You know, is it tall grass prairies? Is it deciduous hardwoods? And that makes a difference in the type of soil that you get. And of course, the topography. Is it an upland, hills? Is it a stream terrace? Is it uplands here on the Less Hills where we live? Oh, the other thing I was going to say about 12, this over limestone. When you see limestone as the residuum, that would be indicative of a possibility of sinkholes. So they do have quite a bit of sinkholes in this area. The what's the name of that river that disappears?
The Lost River.
Yeah, the Lost River is over in this area of the state because it goes down, you know, down into the limestone areas and then it'll come back up somewhere else. So this is very typical of limestone. It's soft rock, dissolves rather easily in geological terms. And the next thing you know, you get a hole in it and the land caves in around it and you get a sinkhole or something like that occurring. They call that the karst topography. When you get out of, and this is kind of a northern finger of it, when you get out of Indiana down here into Kentucky, the karst topography explodes. It's a very, very large region of central Kentucky. The Mammoth Cave area, of course, developed in that karst topography and the limestone deposits and so on. So at any rate, let's go back to some of the basics.
You want to back up?
Yeah. Can I do that and start over? Okay. So, oh yeah, here we go. Cool. Yeah, I don't remember where I was supposed to start.
Yeah, right there.
Right there? Okay. So let's back up a minute and just talk about, get the thing going here. What is soil? Of course, soil has a mixture of solid space and pore space in it. So if we could take a slice of soil out of the, run out here with a shovel or something and get a really thin slice of soil like a sheet of paper and hold it up, there'd be a lot of holes in it. And we'd see that pore space in there, about half solid space and half pore space. And so the typical average run-of-the-mill soil that we have, we call them mineral soils, about 45% mineral. We'll never achieve 5% organic matter in most of our soils, and more like 2 or 3, and the rest would be the mineral fraction. And then the pore space is the other half. That would be the other 50% of the soil. So half of it's got holes in it, got space in it, and half of it is solid material, most of which is mineral. And so the pore space, of course, can have air or water in it. Right now it has mostly air in it. It hasn't rained forever. And I wouldn't say we're in a drought, but it's really, really dry. It's abnormally dry in most of, at least here where we are. And so we probably don't have over about maybe 10%, 5 to 10% moisture right now in our soils, and the rest of it's all airspace. And so when it rains, then that space will fill up with water, and we'll go to like 80 or 90% water until it drains out. And then, so that's what these arrows indicate, is that's in constant flux. Depends if it's raining or not, what the drainage is like, and so forth. But on average, that's a pretty good rule of thumb, that soils are about half space and half solids. Texture refers to the proportions of the different particle sizes, sand, silt, and clay. Organic matter, you'll notice, is not on that list. People get tripped up on that sometimes. But the technical term, the technical soil term of texture means what are the separates. How much sand, how much silt, how much clay. Doesn't have anything to do with organic matter or the color or anything like that. So you can have a sand that's kind of red, you can have a sand that's black, but it's still a sand. And so that is simply, texture is a pretty simple way to define the physical characteristic of the particle sizes. Loam is a mixture of all of those. And so loam is kind of this typical dream soil that you want for your garden, that's well drained, and on the other side of the coin it does hold water because it has the right mix of particle size. If it's got too much sand, it drains, like our sand hills we talked about. If it has not very much sand, it has a lot of clay, it holds too much water. You know, it doesn't get enough air in it a lot of times for appropriate, you know, for your garden crops, or even for my interest, my agronomic crops. So loam is kind of this perfect soil that has a mixture where all three of those express themselves equally. Yeah, there we go. If we look at the soil texture diagram, then we have, I don't know if we can get that off of there. Oh, maybe we can move it. Oh, there we go. You look at your soil texture diagram, we have, in general, clay across the top. We got a sandy clay, a regular clay, and a silty clay. Through the middle, more or less, we have clay loam. Oh, sorry. We have sandy clay loam, and silty clay loam. And then across the bottom, we have our loams. So we have either sandy loam, which is the tip towards the sand side, or we have silt loams, which are kind of our ideal soil. I would say these two are the prize soils for crop production and gardening would be loam and silty loam, because we like those because they have a nice mix of particle sizes. They hold enough water to be meaningful for a long enough period of time so it benefits the crop. But if you get a bunch of rain every day for a few days, after that finally clears off, they drain pretty well. You know, after a few days, that excess water is gone, but it's still holding water for the plant. And we have two categories of sand and loamy sand. Now, let's think about this for a minute. In order to get the sand category, which is way down here, you got to have a lot of sand. You know, it doesn't even start until you get to 70% sand. I guess I should back up a minute. This thing represents the percent sand, percent clay, and percent silt, which are the components of soil texture. So you got to get all the way over here above 70% sand to get into the sandy category. It's right down here in this corner. And you got to get up to, you know, like 85 or 90% to get into the pure sands. So there's a lot of sand in that, not much else in that. It's mostly sand. It's less than 10% clay, and it would probably have less than 10 or 12% silts, you know. I mean, it's just right down here, predominantly sand. Let's compare that to clay. When we get up to 35% or more clay, we're into the sandy clay. If it's above 40%, we get into the other ones. So it only takes 40% or so clay to get into the clay category. It takes over twice that much to get you into the sand category. So, as you know, little clay goes a long ways. If you've ever been in a muddy field or tried to walk around where it's muddy, or your car runs off the shoulder of the highway and there's a high clay, unprotected shoulder there or something, man, it just sinks. It goes right down, and there is no way you're going to get that out of there. And the clay is going to be sticking to everything. If you're walking in clay, it sticks to your shoes, and the more steps you take, the bigger they get, because clay sticks to itself. It's cohesive. And so clay has a lot of unique characteristics that the sands and the silts do not. So it doesn't take a lot of clay for it to express itself in the textural sense. So if we have equal expression of sand and silt and clay, we have a loam. So the loam is sitting right in the middle. Well, how much sand and silt and clay does it take to get a loam soil? Well, if we go across the sand here, we got 40%. Go right up here, that puts us in the middle pretty much. If we're looking at silts, we come down here, 40%, come right down the line. These read on the line, on the lines that are drawn. So make sure you're following them in the right direction. And so we get to silt, 40%, comes down here to the middle, but it only takes about 20% clay. So clay expresses itself much more strongly than sand and silt. So it takes twice as much, whoops, I messed that up, sorry. There we go. So it takes twice as much, what am I doing here? There we go. It takes twice as much sand and silt to get the same expression as it would for clay. So your typical loam soil is 40% silt, 40% sand, and only 20% clay. If we have equal amounts of those, what do we get? If it's 1/3 sand, 1/3 silt, and 1/3 clay, where do we end up here? That would be equal amounts. Well, try not to hit the wrong button here. 33% clay will come right around in here. 33% silt would be coming down this way, and 33% sand coming up this way, and it hits us right in the middle of clay loam. So equal amounts of each of those particulates will express as a clay loam, but if they all have equal expression, that is 20% clay and 40 of the other two, then we end up in the loam category. Okay, so that's kind of a quick overview of texture. Structure is the way the soil particles are put together. What's our time here like?
We go 9 to 10:15.
Okay, good. So structure is the way the soil particles are put together. So remember, texture is how much each one of them things we have in it. Structure is different. Structure is technically how the soil aggregates are put together. And so that sand and silt and clay has to go together somehow, but that won't happen by itself. So now enter organic matter, or the biological system of the soil, and you get organic matter has an overwhelming influence on structure, as does the amount of clay. And also, because soil is a biological system, of course, we've taken that inert mineral pile of stuff that was left behind from whatever geological activity there was, and it's invaded by microorganisms and lichens and eventually grasses, and over eons of time you get a mature hardwood forest or something like that. Well, that's a biological system now. It's got a lot of biology going on in there. It's got a zillion different kinds of microbes. It's got plants growing all the time, and so we get organic matter coming into the system. We have a lot of chemical reactions that form other compounds that are in the system, and those the debris from the microorganisms that grow and die off, and chemical oxides and organic material. There's a bunch of substances in there. They all cause that structure to form in different ways. So we have a platy structure, a prismatic, a blocky, and a spherical kind. Let me see if they have a picture of that. Is there a picture of that in here? Do you remember? Okay, that's kind of what I wanted to. Whoop.
And if I don't have a picture, I go out and Google one.
Yeah, well, I've got one on my flash drive.
And you can pull that up.
Yeah, I never did get it going. Hang on a minute. Bear with me, guys. Started talking before I was ready, but that's all right. Okay. Oops. I don't know if that's going to start or not. Yeah, there it goes. Let me hit this one right quick. So when we were talking about sand and silt and clay, that represents their various sizes. Sand is many, many, many times larger than clay. It takes an scanning electron microscope to see a clay particle. They're really, really, really small. Silt particles are pretty small as well, but they are bigger than clay. And depending on whose book you're reading, they have different ways of categorizing sand, silt, and clay. I like, let's see, which one do we use? Excuse me, we use the USDA scale. Clay is less than 0.002 millimeters in size, so it's pretty small. Silts go up to 0.05, and then sands are between 0.05 and 2 millimeters in size. And we have, of course, the different categories of sand in there. And so we've talked. Now, I guess one other thing I should mention, clay is a secondary mineral, so it takes a chemical reaction of some kind to get clay. Sand is really tiny pieces of whatever the original rock was. So quartz, sand is mainly quartz. And if it was sandy stuff from soft minerals, it's probably already degraded through chemical reactions. But let's just say sand is quartz because that's mainly what it is. It's what they make glass from. So, and silt is really small particles of sand for the most part. And so those two things are pretty inert. You know, I mean, you make glass from quartz, and glass is inert, put strong chemicals in it in the lab, and you know, it can hold that. So the sands and silts provide a physical property to the soil, which is very desirable in terms of the soil structure and the soil texture, the tilth of the soil. The clay, on the other hand, has undergone a chemical reaction, and it has become a plate-like structure which is built around silica oxygen tetrahedron. We won't go into that, but it is, I just want you to know that it's flat. Okay, sand and silts tend to be kind of round, irregular, not perfectly round, but irregularly round, I guess you'd say. Clay is like sheets on your notebook. It's flat. It has a high specific surface area. It's pretty light, but it has a lot of surface area there. You know, a sheet of paper doesn't weigh much, but if you measure, you know, your 8.5 by 11 sheet of paper and do the math and calculate the square inches there, there's a lot of square inches for a little bit of weight. And that is not the case for sand and silt. So clay is a different kind of mineral. It's a secondary mineral and has undergone that weathering or chemical reaction in the soil, sometimes mediated biologically, and it's really small. And so you can't hardly even see it on the picture. There's a few little specks up there, and that would be the relative size of clay compared to sand or silt.
Dr. Mansfield,
Yeah.
I want to tell you, when we did sedimentary rock, we used Wentworth scale,
Mm-hmm.
and so the bottom for the sand in a sandstone is 0.0625.
Okay.
So it's interesting that your bottom was 0.05.
Right, yeah. And in my world of agronomy, we pretty much stick to the USDA scheme of things, but you can see that the U.S. public roads and people who are civil engineers that are working with this material for engineering purposes, rather than growing plants on it, they have a different way of looking at these things, and your system is a little different too. So, yeah, there is more than one. Okay, here's a picture of some sand grains. So they're just intact, little bitty, tiny chips off the rock, basically. Quartz, feldspar are the main ones in this picture. There's some pore space. There's some silt grains around in there. And then, of course, we can't see the clay on this picture. Okay, let me see here. Another triangle. I think I'm getting close. Well, here's some structural units. And well, I think there's a picture coming up here in just a minute, but let's stop at this one. So here are some pictures of some structural units. Generally in the topsoil, you tend to have those round ones, kind of the spheroid breadcrumb kind of looking things. There's a lot of organic matter in there and a lot of microbial activity, so we have microbial gum and some oxides and stuff like that, along with the organic matter that holds things together. And they tend to be the darker colored, small, spheroid, kind of round kind of particles or structure, granular structure we call it. And then in the subsoil, we tend to have an accumulation of clay that happens in the subsoil. So there is an uptick of clay. We call that the clay bulge, which has a little more clay in the subsoil. Not much organic matter. It's way down there. You know, we got some roots that go through the subsoil and those extract water, but a lot of those roots don't contribute at the end of the day a whole lot to the accumulation of organic matter, especially in trees, because tree roots live a long time. They're not unlike the prairie grass roots, which grow and die off every cycle. But in our world of deciduous hardwoods, there's just no way to get a bunch of organic matter down there. But we do have the clay, and so we tend to have a different structure. So clay is driving a blocky structure more than the round one. Oh yeah, here's my picture. Okay, so topsoil, and this is more or less arranged in profile. So this would be your topsoil, would be your spheroid, granular or crumb. The bottom line is that they're rather small and round, have organic matter as the main actor here, humus, that is, that make them that way. There's a plate-like structure, which sometimes we see in soils and sometimes we don't. The platy structure is common in what we call the E horizon, kind of just beneath the topsoil. Platy structures can arise from several different ways. They can arise from just the fact that in deciduous hardwoods like we have, you know, native vegetation here, we don't have a lot of organic matter down there. If you think about a forest ecosystem, every fall, like now, here over the next month or so, all those leaves are going to come off and go onto the forest floor, and the microbes and the flora and the fauna that are found there, some of the little worms and all that teeming mixture of biological activity is going to incorporate that. It's going to decompose, and it will end up in the top part of the soil. And that cycle happens over and over. So the leaf litter in the fall tends to be incorporated in the upper few inches, or let's say the upper 8 to 10 inches of the soil. It doesn't get down there anywhere. There's no activity down there. There's nothing that'll pull it down there that low. On the other hand, we have a prairie grass soil. Tall prairie grasses have roots that may be 4 or 5 feet deep. And then every fall, a portion of those roots will die off to the crown. So now you have this organic material extended throughout the several top feet of the topsoil and decompose, and they form a thick topsoil. So our prairie soils, like we have going across Illinois into Iowa, tend to be really dark. You know, it's that flat ground. It's really dark soils, and they're very, very deep because they developed under prairie grass vegetation. You'll never get that where we live under deciduous hardwoods. And they would not have an E horizon, or that platy structure. They would not have a platy structure in those soils because they have too much organic matter throughout the upper few feet of the soil profile. But in our world, in you know, deciduous hardwoods, we'll often have a platy structure underneath the influence of the incorporation of the leaf litter. And it will be devoid of organic matter. It'll be really light in color. There's nothing to put those things together in any particular way. And for some reason, they form these flat plate-like structures. Then we get into the subsoil where we see blocky structures, and some of these others prismatic. We can have prism. I've never seen the flat top ones here in the forest. I think it takes other kinds of vegetation maybe, or different climate, but we do have some of these occasionally, but not a whole lot. Mostly we have this. We have block-like structure in the subsoil, and again, clay is the main thing that puts them together that way. They're down there in the subsoil. Clay is a secondary mineral that's formed at the top of the soil, and it percolates down through the soil profile during thousands of years, and it gets stuck down there. And that cycle happens over and over again when the soil is developing. So the clay that is in here, in this subsoil, forming those block-like structures, was not there originally in the original deposition. That clay is a secondary mineral. It forms at the top of the soil where you have the intense biological activity, and then it alluviates, or it moves with percolating water and until the water slows down long enough to drop it off, and you get a bunch of clay in the subsoil. So our high clay subsoils, generally speaking, I mean, it is possible to get that from a deposition, but it doesn't happen very often. Normally it's due to the movement of those clay particles into the subsoil, which gives us the block-like structures. I think that was the main thing I wanted to show you there. There's just pictures of PEDs here and structures in a subsoil at B horizon. There's a big one. There's some small aggregates of spheroids from topsoil. I probably ought to back out of this because I don't know where I'm going here for sure. And we'll go back to any slide. Oh, wait a minute. This one I wanted to show you. Okay, almost quit too soon. All right, so texture, remember, is simply the amount of sand, silt, and clay that's in the soil. Structure is really complicated. Structure is how they're put together. And it's really complicated how they get together. And we have here a picture of a macro aggregate. We can see some little tiny branch roots, some fungal hyphae. There's a team of microbes in there chewing away on stuff, producing microbial gum. Chemical reactions are chugging along, making oxides as a spin-off, and all of that stuff is helping to form the aggregate. And then we can take this little box here and blow it up, and now we see our root going through there with the branch roots on it, root hairs, I guess it would be, fungal hyphae, and then we got some polysaccharides that are around due to the microbial activity. And then we take a little piece of that and blow it up, and we get a next look. We're drilling down into that aggregate now, looking at it closer and closer. We have some mineral grains with microbial debris, plant debris coated with clay. So now we're getting silt encrusted with debris and some other things going on there, some clay forming along the some plant and microbial debris encrusted with clay. And then we take this little corner right down here and blow it up, and we see some sand, some silt grains, clay and humus domains, and that's key here to the formation of these aggregates, because clay and humus are charged. And they're both, clay is negatively charged, so is humus, and so they attract cations in the soil, and therefore they glob together around these cations. Now they're both negatively charged. In the absence of cations, they would not associate with each other because they would be repelling. But the cations like calcium, magnesium, and things that are in the soil cause them to glob up to each other, and clay and humus really like to hang out together. They pair up in the soil there and provide some adhesion and some bridging between the particles and stabilization of aggregates. Oop. So, in contrast to texture, structure is really complicated. And it takes a long time to build structure in the soil. And I don't know if any of you are involved with agriculture production. Maybe you know that federal programs right now are driving pretty hard on the soil health issues, and no-till, reduced tillage, cover crops. All of that is supposed to, and it does, help to improve soil health. And this is one of the things they're trying to do. They're trying to build stable structure in the soil. And you do that by infusing organic matter. And so if you go way back, when I was your age, a long time ago, tillage was all the rage, man. I mean, everything was about tillage, and large equipment and tillage, and more tillage. Well, every time you till the soil, some of that organic matter oxidizes. And the next thing you know, you don't have a lot of humus in the soil, and what happens to your structure? Well, it's not so good anymore. It's not stable, as stable as it could have been otherwise. And so that's the movement towards no-till, reduced tillage, conserving residues, incorporating cover crops, providing that green bridge in the winter. All those things are to drive this process of establishing stable soil structures. So the other thing I was going to say about structure, and then I'll get back to your slides, if you have soil that is wet, and there is, again, I'm coming at this from my agronomic perspective of field crop production, but if the soil is wet and there is some trafficking on that soil, you know, or from early planting, or maybe there's a bunch of rain during harvest or something, and you drive equipment on wet soil, the structure is squashed. You lose that good structure. And you get what we call a compacted soil, which causes that plate-like structure, or the plate-like texture. You get platy, those little platey things formed in the soil. They can form artificially from soil compaction. And so to remediate that, of course, we want to maybe try to break it up when it's dry with some subsoiling. We want to plant cover crops. We can apply animal manures. We can get that system going again by adding organic matter in the form of cover crops or animal manures, and then let nature run its course to rebuild that profile, that structure. It doesn't happen overnight. It might take 5 or 10 years for stable soil structures to develop. So, you know, they've been sometimes degraded through mismanagement of soil, and so the federal programs today are all about soil health. I'm sure you hear a lot about that, and cover crops, and that's what they're attempting to do, is kind of rejuvenate that soil structure. Okay, and I think I better quit on this one. So let's see. Penny, let's see, what do we got here? So yeah, the soil structure and the texture both have a big influence on how easily the soil is cultivated. Our sandy soils, of course, don't pose a lot of resistance to tillage equipment, whereas our high clay soils pose, of course, a higher resistance to that. If I start the program, it'd be better. Okay, there we go. So we have the different kinds of parent material. I think I've alluded this to a little bit already. We have the residual parent material in the bedrock, and we talked about the karst topography and the limestone and sandstone and shale we have in south central Indiana, versus our transported parent material, which we have here in the terms of windblown silts. Those are our loess deposits, or we have water deposits, alluvial deposits along the waterways, and we have our aeolian sand. So wind and water are the main forces of transport for our soils. You get into some other landforms, you have really steep areas, and soil debris can fall off those cliffs and accumulate in the valleys, and so that would be a gravity transported. We don't have a lot of that. For us, it's mainly all about wind and water. Time and the amount of time to evolve varies for different soils. The soils of south central Indiana, if you go back to remember that map that we pulled up, those are really old soils, so they've been there a long time. And those residual soils are developed, more highly developed in the subsoil. They even have a fragipan, some of them, which takes a long, long time to get. Our younger soils tend to be on the floodplains and the terraces because, like we said earlier, water comes and goes. We live right next to the Wabash River here, and you see it flood sometimes, and then right now it's pretty low. And then this winter it'll probably flood, you know. So there is some annual flooding that goes along the waterways, and those soils tend to be very young because they're in a state of flux. You know, material is coming and going. It's not stable. And loess hills are medium. They're kind of in between. The glacial till plains of central Indiana, those would be a medium length of time. And we're talking geological time here as far as their development goes. Climate. The climate for us here in the Midwest is all the same. We live in a humid temperate climate. So humid means we get more rainfall on an annual basis than the soil can actually absorb, or that we can actually evapotranspirate back out of the soil. So we get extra, on an annual basis, we get extra water. And of course goes into our waterways, accumulates in the low spots, it percolates through the soil, and so that's a factor. The other one is temperate, which means it's not too cold and it's not too hot. Now we're talking about average climate. We're not talking about weather. I mean, it can be 100 degrees in the summer and 20 below in the winter. You know, that's normal. But the average temperature is moderate, you know, and that's what climate is all about, is average temperature. So if you live in Central America somewhere, your average temperature is pretty high, you know, most of the time. They don't have much of a winter down there. In fact, they don't have any. You live in the lowland tropics, it's hot all the time. So and it may rain a couple hundred inches of water a year. So that climate is a driver on the soil development processes. Plants and animals, we alluded to that a while ago. I think I compared the prairie soils, which have the tall grass prairies, which is a very different ecosystem than where we live here with deciduous hardwoods. The native wildlife is different, you know, in the woods as it is in the prairies. And so that system of plants and animals is having an impact on the way the soil develops. Trees root different than prairie grasses. You know, trees have long-lived, permanent root systems. They can be very deep, but they don't die off every year. I mean, they may lose a root once in a while, but not very often. Tree gets bigger, it just keeps growing more roots, but doesn't necessarily lose all of the older ones. Prairie grass cycles a good part of its root system every year. This fall, when it gets cold out there on the prairies, the native grasses that are there, a lot of those, you know, of course, the tops die back to the crown for sure. It's really cold. But a lot of those roots will also die back to the crown. Not all of them, but some of them will. And then that whole process starts over next spring. Sprouts a bunch of new roots, and the grass starts to grow above, you know, again. Topography is another one. The steepness of slope often have, if the soil is steep, it often has very poorly developed soils because as soon as soil processes begin to form soil, and you get a bunch of hard rain, where does it go? Well, it goes to the valley floor. And so slopes tend to have shallower soils than the soils at the bottom in the valley. So the valley soils, the lowland soils tend to be thicker soils, and if they're well drained, very optimum for growing plants. Orientation, that is the direction the slope is facing, not a big deal here, because we don't live in the mountains, but then you get out west in the Rocky Mountains, that does make a big difference, especially they have those prevailing winds that come off the Pacific, and they go up and they dump a bunch of rain, and it gets over the mountain and it's kind of drier on the other side, and some of those north-facing slopes would be in the shade. They'd have a little more vegetation than a slope that faces to the south. Not a big deal here for us as far as soil temperature and moisture, because again, our hills are pretty small and don't have an overriding influence. For us, it's more about water, I think. But no, I should back up. Topography does have a big influence on the soils. For example, the soils that develop in the low flat areas are going to be very different than the soils that develop up on the hills. So. Okay, let's see here. No soil development, too steep. If there's a valley floor out there somewhere and the stuff is transported and deposited there and there's nowhere else to go, it just keeps building up and it gets to be a really nice, productive soil. And that would be, I guess, and correlated to the landform would be the fertile valley here along the river. And the steep slopes up here, not much going on there, you know, a little, and this is obviously a western landscape. Then you have your thicker soils developing on the flat terrain as compared to the thinner soils on the upper part of the terrain. Oop. Well, that wasn't the right thing to do. Oh, yeah, I need to do this. Okay, one click. So the soil profile, this is pretty important here as far as the horizons go. I should have showed you that on my other, well, I had it up there and I forgot to do it, but these are what we call the master horizons in the soil profile. The O would be the organic matter, so let's go back to the woods here. Go back to into the woods around here somewhere, and when you go in there, you notice that you're always stepping on leaves. And if you move that over a little bit and just kind of scrape it off, there's a thin layer of really dark, mostly decomposed organic material, because the leaf litter from the last few years is underneath there, and it's direct contact with the soil, and it's being decomposed by all the intense biological activity that's going on, decomposing that stuff, and it develops this little thin, really dark, mostly humus organic layer that sits right on top. And then the macro fauna, the, I don't know, the centipedes, the earthworms, a lot of those larger soil ecosystem little animals there, termites maybe, you know, termites are chewing up trees. Well, they'll kind of mix that in then in the top few inches of the soil. And once it gets mixed in with the soil, then we have the A horizon. So the A horizon is the top horizon of the soil once you get under that little thin bit of leaf litter that's on the top there. So that we are into the soil now with the A horizon. I'm going to skip E. I'll come back to E. So let's go from A to B. A would be topsoil. B would be your subsoil. And you'll notice that B is called the zone of accumulation. And that's where all the clay goes. Remember we talked about the clay? It's formed by the intense biological activity at the top of the profile or the top of the soil. And then it, due to those reactions, the clay is formed, and then the percolating water moves it down. And that's what we call about a zone of accumulation. It's accumulating clay. It accumulates some of the oxides and some of the other byproducts of those intense biological activity reactions on the top of the soil, and it ends up in the subsoil. So B would be your subsoil, zone of accumulation. And then underneath that, once we get far enough in there, you know, 4, 5, 6 feet, whatever, then you'll find something that looks like what could have been the parent material. And so that would be very, very slightly altered parent material, and if you keep going, you might get to the bedrock, or you might get to that original deposition of some kind. And so the soil is building on that original geological deposition that was there due to the intense biological activity, the plants invade, all those things, and you get this soil profile forming, and these are the master horizons that you would get. Now, what's this E horizon? It's not lettered in sequence, you know, and so we go right from A to E before we get to B. Well, E is the last thing that happens normally. Normally you'll get an AB soil first, and then if it goes on for enough eons of time, you'll get this little E horizon showing up in there. And E horizon is a zone of leaching, eluviation, which means loss. It is a zone of loss. So it doesn't accumulate anything, and it loses stuff, okay? So it's things are leached out of it. Any clay it's close enough to the surface that there's some intense biological activity going on. Maybe not as intense as on the very surface, because there's no humus in there. But the clay just keeps going. You know, any clay that's formed there is lost. Any clay that's formed above it just keeps going and ends up in the B horizon, or the subsoil. And so it's not accumulating anything. It's below, you know, in the woods, we have that organic layer, and we've got that mixing of that in the topsoil, but the topsoil isn't very deep. You know, it could be 6, 8, 10 inches deep, and that'd be about it. Well, right underneath that, then you have the E horizon. It's too deep to be affected by the mixing activity of the organic matter. So it doesn't accumulate organic matter. It's losing clay, and it's just this little thin, it's usually not very big, it's usually pretty thin, light-colored, nondescript, plate-like structure that just sits right in the middle there between the A and the B horizon. But it doesn't occur until you've moved pretty far down the road. You'll get an A horizon over a B horizon in a younger soil, and eventually, over a few more eons of time, this little E thing will kind of start to show up. So in our typical upland soils here in Knox County. Remember, we have those lust caps. And those are medium soils. They're not really very old, and it's really, really hard to find an E horizon in them. You can, but they're really weak. Sometimes they're there, sometimes they're not. So we're right on the verge of having soils that are old enough to find those E horizons on a regular basis. Now I don't know if any of you go to Robeson Hills. If you have a class that goes over there, I think they go over there, and some of the biology classes, they kind of dig around and see if they can find some of those, and sometimes they do and sometimes they don't. So, but these are the master horizons. You should know them. O is your organic horizon at the very top, really thin. A is the topsoil. B is your subsoil. C is the partially altered parent material that's at the bottom down there, and then your E horizon comes in between the A and the B. And that's your zone of loss or zone of leaching. Here's a good picture of them. Here's your little A horizon there. It's not very thick. It's just some kind of loose, partly decomposed, decayed organic matter. The A horizon is dark because it has the organic matter mixed in. The B horizon is blocky structure because it's got the clay accumulation, and we call that an alluvial horizon of our subsoil. The E horizon is technically, I don't know if they have it, I can't see mine very well. Well, they don't have it in topsoil or subsoil, either one, so they just have it as the zone of alluviation. I think most people would probably put it as part of the subsoil because this doesn't have much going on with it up here. And then you have your C horizon, which is the partly altered parent material, and here's your unweathered parent material with some kind of bedrock or something down here. So once you get under all of that, you get down to that original whatever it was that it developed from. So this is a really nice picture of the soil horizons. The solum is this upper part up here, sometimes referred to, as that combination of subsoil or topsoil, subsoil, and anywhere that you've got some activity going on would be part of that solum there. So classifying soils taxonomically, there is a whole science around soil classification, and it looks at the physical and chemical properties of the profile, and their combinations of Latin and Greek words normally. It's analogous to, I guess you'd say, the plant classification system where you have scientific names for plants. They have scientific names for soils. I don't remember if they have them in here. Well, they have a few. Well, they have the soil orders. It's really hard to see a lot of detail on this map, but you can see in general what's going on. We generally have in the humid eastern United States, we have alpha sols. That's the first one on the list there. Alpha sols are moderately developed, generally speaking, and have a rather medium level of weathering. Weathering, the biogeochemical weathering that we talk about, is a way to describe the intensity of weathering and the development of the soil. So our soils tend to be moderately weathered, and that falls them into the alpha sol taxonomic order for a lot of other reasons too. But then we have, let's do ultisols. If we go from here to Georgia and start moving into the southeastern United States, what happens? Well, rainfall increases, length of summer increases, winters are milder, so the average temperature is higher, rainfall tends to be higher, and what's driving the biogeochemical weathering? Temperature and rainfall. So they have more intensively weathered soils as we get into the southeastern United States, which develops different kinds of clays in the soil. We have more of the kaolinitic clays, we have more of the marlinitic types, smectites, I guess you'd say. So it's a whole different way of classifying those soils because they're at a different stage of development. So that lower base saturation, the different kinds of clays and so forth, tips them into the ultisol category. And then if we go west, we get into the mollisols. That's those green ones there. And those are the prairie soils. Really thick A horizons, high base saturation, subhumid climate, because you know we're humid temperate here, and you get far enough west it becomes subhumid because they don't have the amount of evaporation, transpirational demand that they would have out there is actually higher than the rainfall. So that would be subhumid climate. And that combination of rainfall and temperature drives the native vegetation. So we get trees because we're humid temperate. The western states get grass because they don't have enough rainfall to sustain forests, so they get prairie grasses in the subhumid climate. And of course that then affects the soils that they would have, and we throw them into the mollisols. Let's see, what's another common one would be oxasols, and we'd have to go to the true tropics to get those here in South America or Africa. And you'll notice those are right along the equator, so it's pretty hot there all the time. It could be 90 degrees every day. It might rain every other day. May have 150 inches of rain a year in some of those areas. You know, 3 or 4 times as much rain as we get. High temperatures, it's never cold. And that really drives the intense biological activity, the geochemical weathering processes, and the development of those soils. So that's a completely different array of clays, the way the organic matter behaves in combination with those clays, and so on. So again, another way to classify those would be in the oxasols. That gets most of that gets really the common ones. Well, I guess we can go to the desert here and do the iridosols, as the arid prefix on that implies. It's pretty arid, and so not much going on out there. It might be hot all the time, but there's not enough water to drive much in the way of biogeochemical reactions. So yeah, it's hot, but it's not wet. And so it's a different, thing altogether. And of course, you would know that if you've ever driven through the western United States, or even if you've flown over it in a plane, you can see it from an airplane that it's very different landform and everything. Here's the desert. Let's see what else. Well, gelisols, those are the ones that have permafrost. So as you might expect here in those northern areas, there's layers down there in the soil that are permanently frozen, and the tops will thaw out in the short summer season, but it never thaws out beneath that. So those are very different. Northern Canada, Alaska has a bunch of those as well. Let's see, probably enough on that.
Put that in there.
Yeah, that's fine, yeah. So we have, now this is the map, no it's not, this is a different one, but Penny mentioned that we do have a VU soil judging team, or she talked about the high school judging event that we do. VU does have a soil judging team. I'm not the coach for that. We have a soil scientist, because soil judging is all about land use and appropriate land use. He's a pretty good soil morphologist and a practicing soil scientist, so he actually coaches our team. If you have interest on judging soil and learning about appropriate land use for housing or for agricultural uses. And then, of course, you can do that on, if you transfer up to a 4-year school, they'll all have soil judging teams. And then that's kind of the feeder program for practicing soil scientists, or if you want to work for DNR or NRCS or something like that in the soils arena. Most of those guys that work in these agencies or work as practicing soil scientists at some point in their career through high school and college did all the soil judging stuff and learned all the stuff about soil morphology and how to look at that soil. It's all about looking at soil characteristics, maybe doing some chemical analysis, and then making the appropriate land use decisions about, you go out here, would you be out of college in a few years and be making all kinds of money, and you might buy yourself a nice little place in the country, and well, now I got to get a septic that's going to work. Well, who's going to do that for me? I build my house out there. Well, a soil scientist is going to do that. And the laws in Indiana are such that it has to be a licensed practicing soil scientist has to approve your septic system. So when you flush, it works. And one of these days, your kids may live there, and you want it to keep working, for the duration of that. And so that's one example of what practicing soil scientists would do is they do work a lot with landowners and appropriate, application of the science to make sure septics work and things like that. I think it's dangerous if they don't. Let's see. What are we looking at here?
That's the physiographic map.
Oh, physiographic map. Okay.
For your soils map.
Yeah. Okay. So we got the different names of the areas there. We're in the Wabash Lowlands here. So we're what's our elevation? 400 to 500?
Oh, we're around 400 here.
Yeah, we're around 400 here. So we're in an inland lowland spot. We're a long ways from any ocean, but we're at 400 feet above sea level. So it's subtropical in that sense, I guess you'd say, and we feel it every summer. Here's your soil regions. This is the one we looked at earlier. Soil characteristics, climate slope.
Yeah, most of this you went over. We're right at 10:15. There was one more slide with a picture of contour mining. I thought we would end on.
Okay, that's fine. Yeah, soil erosion, again, I've kind of alluded to this earlier, but soil erosion is a real problem on our upland soils around here. Our high silt, rolling hills, lust caps, high silt, organic matter, tan colored soils. They're really good soils. They can be very productive, but the Achilles heel, of course, is water erosion because of the relative low organic matter content and on the slope. And silt has a really bad habit of washing. Man, when silt gets going, you can't slow it down hardly, can't stop it. So that's the other reason, of course, that the federal programs are pushing the cover crops and things like that. It is about soil health, but it's also about controlling soil erosion with reduced tillage and conservation tillage and all that. So we also have wind erosion problems on our sand hills, which is kind of unique for us because wind erosion only occurs, we think of wind erosion as happening in the desert, but it does occur on the sand hills.
It's that next slide up there.
That one?
Yes.
Okay. So, yep, ways to keep track of the soil, keep it where it belongs. It takes about, I don't know, what's the rule of thumb, 500 to 1,000 years to get an inch of topsoil. And so you can lose that much easily in a generation of mismanaging. So, over a 20-year period, you could easily lose an inch of topsoil, but it's going to be 500 to 1,000 years before you get it back. So the soil, it is a delicate resource and does need to be conserved. Some farmers, I know, again, I'm going back in time more from my generation, weren't too worried about it, and they would just buy more inputs. Well, you can't keep doing that forever because the next thing you know, you're farming in the subsoil, and you can't buy enough inputs to make up for that loss. So, very good.
Well, we'd like to thank you once again.
Thanks. Appreciate it.